In the main video, for this problem, we obtained this result for a sub x, and we obtained this result for capital D. And we did some work to check that those results made sense. We saw that the role of mu k in this expression makes sense, and that the roles of v naught and mu k in this expression for distance made sense. But there were also some issues that we didn't talk about. We didn't talk about the role of little g in either of these two expressions. And we didn't talk about why the given v sub naught is missing from the a sub x expression. And we didn't talk about why the given for mass is missing from both of these two expressions. So in this optional supplemental video, I would like to go into those deeper issues and analyze more deeply why these results make sense. This video is intended for students who are interested in getting some extra tools for checking that your results make sense and checking whether you've made a mistake, and who'd like to get a deeper insight and a deeper understanding into the physics concepts. But the techniques in this video are certainly not necessary for solving the problem, so if you find the material in this video to be too confusing, you don't have to continue with it. This video is going to be a long, slow, and repetitious video in order to help students who find this material to be challenging. But if you find that the video moves too slowly for you, you can find a discussion of the main ideas in the video in the solutions document at the end of the solution for this problem. And as usual, you can find a link to that solutions document in the video description box. Okay, so in the main video, we showed that the role of mu sub k in this expression for a sub x makes sense using this analysis. So to begin, we need to try to explain the role of little g in our result for a sub x. Does the role of little g in this result make sense? Does it match common sense? So we can go ahead and ask whether the role of little g makes sense in that expression. So according to this expression, if you increase little g, what would you expect that would do to a sub x? And here again, now we assume that we're holding mu sub k constant. If we increase little g and hold mu sub k constant, mathematically what is implied? Does that mathematically imply in this result that the magnitude of a sub x will get bigger or smaller? I hope that was easy for you to figure out. Little g is on the right side of this equation. If we increase little g and holding mu sub k constant, the right side of the equation would get bigger, which forces the left side of the equation to get bigger, which would mean that the magnitude of a sub x would get bigger. So increasing little g should increase the magnitude of a sub x. That's what's mathematically implied by our result. But does that make sense? So now we want to ask what would make sense. If we redid this experiment with a larger little g, would it make sense for a sub x to get bigger or smaller? You should maybe pause the video and try to figure that out. Now, the first thing that might have occurred to you is that it's impossible to increase little g, because haven't we said that little g is a constant, right? Little g is supposed to represent the magnitude of the acceleration due to the Earth's gravity. Again, don't say that little g is gravity. Don't say little g is gravity. Say little g is the magnitude of the acceleration due to the Earth's gravity. But that's a constant, 9.8 meters per second squared, so isn't it meaningless to imagine increasing this? Well, you can't, little g is a constant as long as you're close to the surface of the Earth. But if you redid this experiment on a different planet would have a different strength of gravity, and therefore a different planet would have a different magnitude of the acceleration due to gravity, and a different planet would have a different little g. So what we're imagining here is, let's imagine that we do the experiment first on the Earth, and then let's imagine that we redo this experiment on another planet with stronger gravity. Well, if we redid the experiment on another planet with stronger gravity, then there would be a greater magnitude of acceleration due to gravity, and that planet would have a greater little g. And would we expect that to increase or decrease the magnitude of a sub x? Now, the logic here is actually a little bit more subtle. That increase in little g would cause a greater magnitude of the weight. So if we move to this planet with stronger gravity, the block would weigh more. On a planet with stronger gravity, the block would weigh more. Remember that in physics, the weight refers to the downward pull that an object feels because of the planet's gravity. The weight force is the downward pull that each object feels from the nearby planet's gravity. It should make sense that if we move to a planet with a stronger force of gravity and a stronger magnitude of acceleration due to gravity, on that planet with stronger gravity, an object would feel a stronger downward pull from the planet's gravity, a greater weight force. And that also matches our formula for the magnitude of the weight force. The formula for the magnitude of the weight force also indicates that increasing the magnitude of the acceleration due to the planet's gravity would increase the magnitude of the weight force. So the first step of the analysis is that increasing little g while holding the other givens constant would correspond to moving to a planet with stronger gravity. And on that planet, the block would feel a stronger downward pull from the planet's gravity, a greater weight force. Now you might think that that should have no effect on a sub x, because remember the weight force operates in the y component, and a sub x is the acceleration for the x component. On a planet with stronger gravity, the block would feel a greater downward pull from gravity, but why should that affect the horizontal acceleration? Aren't we supposed to think about the two components separately? The weight force is a downward vertical force, so why should that affect the horizontal acceleration? Well, we are supposed to think about the x and y components separately, but on problems that involve friction, there is usually a link or connection between the x and y components. The x and y components are usually linked through the normal force. I think we've seen that on previous problems. The normal force operates here in the y component. The normal force operates in the y component to balance out the weight. But the normal force is also going to affect the x component because the magnitude of the normal force affects the amount of friction, and friction appears in the x component. So to repeat, on problems that involve friction, the x component and the y component usually have a link. They're usually linked through the operation of the normal force. On this problem, the normal force acts in the y component to balance out the weight in the y component. But then that magnitude of the normal force is going to affect the x component because the magnitude of the normal force will affect friction, which is going to operate in the x component. So let's trace out how those links will affect the result in this problem. On the planet with stronger gravity, the object will have a greater weight. And if the weight is greater, doesn't that mean that the magnitude of the normal force is also going to have to be greater? The normal force exists on this problem to cancel out the weight, to prevent the object from being dragged down through the floor. So if the weight gets bigger, if the weight gets bigger in magnitude, the normal force will also have to get bigger in magnitude to continue to cancel out the weight. When the object weighs more, the normal force has to get bigger in magnitude so it can continue to cancel out the weight in our y component. We know that the magnitude of the normal force affects the amount of friction. So if we increase the normal force, we're going to expect a greater magnitude of the frictional force. That comes from this special formula for the magnitude of the frictional force, which shows us that when we increase the magnitude of the normal force, we're going to increase the magnitude of the friction. And now, again, this matches common sense. What the increase in the normal force here represents the idea that when the object weighs more, it's going to be pressing more firmly against the floor. When the object weighs more, it'll press more firmly against the floor. But when the floor is pressing more firmly against the object, it's natural that there will be more friction. That should match your common sense intuition about friction that you might have had even before studying physics. When an object presses more firmly against a surface, it feels more friction from that surface. So on this planet with stronger gravity, where the object weighs more and presses more firmly against the surface, it's going to feel a greater frictional force from that surface. But if there's more friction, remember that friction is what's slowing down the block. Friction is what's slowing down the block. and the rate at which it's slowing down the block is the magnitude of a sub x. So if there's more friction, we would expect that the block will slow down faster. More friction will cause the block to slow down faster, and the rate at which the block is slowing down is the magnitude of a sub x. So if the block is slowing down at a faster rate, it'll have a greater magnitude of acceleration. Remember that on this problem, the word acceleration refers to how quickly the object is slowing down. In this problem, acceleration refers to slowing down. So if the block slows down faster, it'll have a greater magnitude of acceleration, according to that physics definition of acceleration. But that matches what was mathematically implied by our result. Mathematically, our result implied that increasing little g should increase the magnitude of a sub x, and now we can see that that matches common sense. Let's go through that logic one more time, because that was more subtle here. On a planet with stronger gravity, we'd have a greater little g. The object would weigh more, so it'll be pressing against the floor more tightly, a greater magnitude of the normal force. And when the floor is pressing more tightly against the object, there'll be more friction, which will cause the block to slow down faster. So the rate at which the block slows down, the magnitude of a sub x, will be greater. And that matches what was mathematically implied by our result. So if we had gotten a result that had said, for example, that little g was in the denominator of this result, hopefully we would have been able to realize that that didn't make sense. It would not have made sense for little g to have been on the bottom of this fraction for a sub x, because that would not match what was predicted by common sense. So hopefully you would realize you had made a mistake if you had gotten this answer, if you had gone through the logic for what makes sense for changing little g. Of course, here worth imagining changing little g while holding all the other givens constant, as usual. Well, this was certainly a more subtle analysis, because this required us to think about both components. So I'm going to go through that again one more time. Increasing little g increases the weight of the object, and you would think that that might affect only the y component. But we've seen that on problems where friction exists, problems where friction exists, the x component and the y component are linked to each other through the concept of the normal force. In this problem, the normal force is determined in the y component because the normal force has to cancel out the weight. But the normal force also affects the x component because the magnitude of the normal force affects the amount of friction, which is in the x component. And that's a typical pattern that you'll see on most problems that involve friction. Most problems that involve friction, the x component and the y component are linked through the concept of the normal force. Please pause the video and answer this question. True or false? The symbol little g stands for gravity. I hope you actually paused the video and came up with an answer, and I hope your answer was false. This is a common student mistake. If I ask a student what little g stands for, they almost always say that little g stands for gravity, but that's a false or a useless thing to say. So please pause the video and answer this question. What does the symbol little g stand for? Again, I hope you actually paused the video and came up with an answer. Here's the answer. So this is a true statement, whereas this was false. It's very important that you have this memorized. Little g is used a lot in physics. You need to memorize what it means. We have to be precise in science, so we need to know exactly what the symbols stand for. Little g does not stand for gravity. That's a false or maybe a meaningless thing to say. Instead, what's useful to say is that little g stands for the magnitude of the acceleration due to gravity. Remember that the units little g is 9.8 meters per second squared. Meters per second squared are the units for acceleration. So we can see that little g is standing for a type of acceleration. The acceleration that's due to the nearby planet's gravity. On the other hand, as we said, if we imagine increasing little g while holding the other givens constant, that does correspond to redoing the problem on a planet with stronger gravity. And here's why. Suppose you have a planet with stronger gravity. If we imagine moving to a planet with stronger gravity, well, if the planet has stronger gravity, then the planet will also have a greater magnitude of acceleration due to gravity, and therefore the planet will have a larger little g. So increasing little g does correspond to moving to a planet with stronger gravity. But you shouldn't take a shortcut and say that little g stands for gravity. That's not precise enough. Little g doesn't stand for gravity. Little g stands for the magnitude of the acceleration due to gravity. In science, we need to be precise about what the concepts stand for in order to use those concepts successfully. Don't say that little g stands for gravity. Say that little g stands for the magnitude of the acceleration due to gravity. Now, I know that this chain of logic here was longer and more subtle than the chain of logic for mu sub k. Some students are going to feel comfortable going through this chain of logic. Other students are going to find that this is confusing, so it's up to you. If you find going through these chains of logic to be illuminating and helpful, well, then I encourage you to keep using that approach. If you find this type of chain of logic to be too long and confusing to be helpful, obviously you don't have to use it. Notice that you could still check the simpler parts of your result. It was relatively easy to see why the role of mu sub k in this result made sense. So you could just check the parts of the result that are relatively easy to check, and maybe not worry about the parts of the result that are harder to check, like the role of little g here. It's up to you. You can go into as much detail for thinking about these issues as you feel is useful for you. So in that spirit, let's go even deeper into checking whether this answer makes sense. What else can we check here? Now, this result only had two symbols in it, mu k and little g. But remember, we had four given symbols. So we could stop to ask ourselves, why does v naught and m, why don't they appear in this result? And does that make sense? So for example, suppose we redid this experiment with a bigger v naught. If we redid this experiment with a bigger v naught, what's mathematically implied by our result? What would happen to the magnitude of a sub x? Well, v naught doesn't appear mathematically in this result, so the result says that if we increased v naught and held the other givens constant, the magnitude of a sub x would be unchanged. Our result mathematically implies that changing v naught has no effect on the magnitude of ax, because v naught doesn't appear in this result. But let's stop and ask if that makes sense. If you really did redo this experiment with a greater v naught, what would you expect to be the effect of that on the magnitude of a sub x? Again, you might want to pause the video and think about that. Well, v naught is how fast the block was going at the beginning of the experiment. V naught was the starting speed. But how fast the object is going has no effect on how fast it's going to slow down, and that's what a sub x is. How fast the object is going has no effect on how much friction there is, so it's going to have no effect on how fast the object slows down. So if we increased v naught, that would mean that the object begins at a greater speed. But that starting speed is going to have no effect on the amount of friction. How fast the object is going has no effect on the amount of friction based on the formula that we've been using. Our formula for kinetic friction, notice, is not affected by the speed of the object. According to this formula, the speed of the object has no effect on the amount of friction. So there's no reason to think that an object that's moving faster would feel more friction based on that formula. And so there's no reason to think that it'll slow down faster or slower. With no effect on friction, there'll be no effect on how quickly the block slows down, and therefore there'll be no effect on a sub x magnitude, because the magnitude of a sub x measures how quickly the block is slowing down on this problem. So we've seen that it does make sense that v naught did not appear in this expression. There was no reason to think that the starting speed would affect how quickly the block was slowing down, and that's what a sub x measures. So we can make a check mark here. to show that we've checked that the role of V naught, the fact that V naught has no role in this expression, does make sense. I think that was pretty straightforward. I think it was pretty straightforward to see that there was no reason to think that V naught would affect A sub x here. Well, we could go even another level deeper and ask, why doesn't the mass appear in this expression? Why doesn't the mass affect A sub x? So suppose we increase the mass and hold the other givens constant. What's mathematically implied by our result? What would be the effect of that on A sub x? Well, the mass doesn't appear in this result, so the result says that increasing the mass would have no effect on A sub x. Increasing the mass will have no effect on A sub x, but now we want to ask, does that make sense? Does that match our common sense? Why doesn't changing the mass have an effect on the acceleration? That's a little bit subtle. That's a little bit subtle and a little bit difficult, but I think we can learn a lot of physics by thinking about that. So I encourage you, if you're interested, to pause the video and try to work out why changing the mass had no effect on A sub x. What is mass? What does it mean to increase the mass of an object? Well, we could loosely define the mass of an object as measuring the quantity of material that is contained in an object. Mass is often defined as the quantity of material that's contained in an object. So increasing the mass would mean redoing the problem with an object that contains more material. For example, say a bowling ball has a greater mass than a marble because a bowling ball intuitively contains more material than a marble does. So increasing the mass can be thought of as increasing the amount of material in the object. Now, how does that affect the behavior of the object? It turns out that increasing the mass has two effects on the behavior of objects. First of all, an object with greater mass is more difficult to accelerate. Objects that contain more material are more difficult to accelerate. And that's reflected on the right-hand side of our Newton's second law equations. Notice that mass appears on the right-hand side of the Newton's second law equations for the x component and the y component. And that reflects the idea that increasing the mass makes the object more difficult to accelerate. That might not be obvious to you, but suppose that we hold the net forces constant. Remember that we're considering here increasing the mass, trying to hold other things constant. So imagine there was a way that we could hold the other forces constant. If we held the other forces constant, and also why don't you assume that everything in these equations is positive to make it easier to think about. Let's suppose all these variables are positive. Well, then if you increase the mass, do you see that you'd have to decrease the acceleration since this side is being held constant? If this side is being held constant, then the right side of the equation has to be constant, so an increase in the mass would have to be balanced by a decrease in the acceleration so that the right side can stay constant and equal to the left side. So you can see that just as I said, an object with greater mass seems to be more difficult to accelerate. It would have a smaller magnitude of A sub x. And similarly, if we increase the mass on the right side of the y equation, we'd have to decrease the acceleration on the right side of the y equation so that the right side could stay constant and equal to the left side. So again, that indicates that increasing the mass tends to decrease the magnitude of the acceleration. And that's the mathematical expression of the idea that an object with more mass is more difficult to accelerate. Remember, we're using the physics definition of acceleration. So that means that an object with more mass is more difficult to speed up, but an object with greater mass is also more difficult to slow down. And an object with more mass would also be more difficult to change its direction of motion. What's important for the problem, on this problem, the object is slowing down. So what matters from this problem is that the object with more mass would be more difficult to slow down. But there's also a second separate effect of increasing the mass. Objects that contain more material also feel a greater downward pull from the weight force. An object with more material that has a greater mass, it turns out that those objects feel a greater downward pull from the Earth's gravity, from the weight force. That's clearly reflected in this formula. We know the magnitude of the weight force equals mg, and that clearly indicates that increasing capital M would tend to increase the weight of a object. Objects that contain more material weigh more, which means they feel a greater downward pull from the Earth's gravity. This is why I said that the mass is a subtle concept, because changing the mass has two different, separate effects. Objects with more mass are more difficult to accelerate, more difficult to speed up, slow down, or change their direction of motion, and separately, an object with more mass also feels a greater downward pull from the weight force. Those are two separate effects of the mass, and they both have to be taken into account. That's why the mass is a difficult and subtle concept in physics. But we can see that the mass has those two separate effects from our mathematics, because the mass appears in two different places in our mathematics. The mass appears in this formula for the weight, for the magnitude of the weight, and the mass also appears in the formulas for Newton's second law. Remember that acceleration is a vector that we think about in terms of components. So we could say more completely here that an object with more mass is more difficult to accelerate in the x component, and it's also more difficult to accelerate in the y component. An object with more mass is more difficult to accelerate in the x component and also more difficult to accelerate in the y component. That's reflected in the x and y equations for Newton's second law. And in addition to that, an object with more mass also feels a greater downward pull from the Earth's gravity. Let's try to get a better intuition for these ideas by considering a specific example of comparing a marble and a bowling ball. So it should be clear that the marble has the smaller mass. And the bowling ball has the greater mass. I think it makes sense that the bowling ball contains more material, so to speak, than the marble contains, and that fits with our definition of the bowling ball having a greater mass. So how does that affect their behavior? Well, because the bowling ball has greater mass, the bowling ball will be more difficult to accelerate. So, for example, suppose that the marble was rolling along the floor. Suppose the marble was rolling along the floor and you wanted to speed it up. Well, it'd be very easy to give the marble a little kick, and that would easily speed up the marble. A marble has a small mass, so it's easy to speed up. Suppose that a bowling ball is rolling along the floor. Can you speed up the bowling ball by giving the bowling ball a kick? Well, yes, but it's a lot more difficult, isn't it? In fact, you might easily hurt your toes by kicking the bowling ball. And the fact that kicking the bowling ball might hurt your toes is a reflection of the fact that it's more difficult to speed up that bowling ball with that kick. It's easy to give the marble a slight kick that will speed it up, but if you give the bowling ball only a slight kick, it won't speed up very much. And if you try to speed it up a lot by giving it a hard kick, you're likely to hurt your toes. So that reflects the idea that the bowling ball with the greater mass is more difficult to speed up. But remember that in physics, acceleration also means slowing down. So the bowling ball with the greater mass should also be more difficult to slow down. And that's true, isn't it? Again, if you think of a marble that's rolling along the floor, it's very easy to slow the marble down by giving it a little kick that opposes its motion. You could easily give the marble a slight kick that opposes its motion and slow it down quite a bit. On the other hand, if a bowling ball is rolling along the floor, it's more difficult to slow it down. If you only give the bowling ball a very slight kick, it won't slow down very much. And if you try to give the bowling ball a hard kick to slow it down, again, kicking in a direction that's opposite to its motion, you might again hurt your toes. So that reflects the idea that the bowling ball is not only more difficult to give a kick to speed up, it's also more difficult to give a kick to slow down. And for that matter, remember that acceleration also in physics refers to changing your direction of motion. In physics, acceleration can also refer to changing direction of motion. Is it more difficult to change the direction of the bowling ball? Absolutely. Again, imagine a marble that is rolling along the floor, and could you imagine giving it a kick to change its direction of motion? So if you gave the marble at a kick that was at an angle to its direction of motion, you could easily send the marble heading off in a different direction. If you kick the marble at an angle that is at a slant to its direction of motion, you can easily have a big effect on the direction that the marble is moving. But if a bowling ball is rolling along the floor, it's much more difficult to give it a kick to change its direction of motion. If you give the bowling ball only a slight kick, it's only going to change its direction of motion a very slight amount. And again, if you try to give the bowling ball a strong kick that is at a slant to its direction of motion, well, then you might hurt your toes again, which reflects the idea again that the bowling ball is more difficult to change its direction of motion because of its greater mass. So I hope this example helps you to see that objects with greater mass, such as the bowling ball, objects that contain more material, really are more difficult to accelerate. That is, they really are more difficult to give a kick to speed up, they really are more difficult to give a kick to slow down, and they really are more difficult to give a kick to change their direction of motion. Another thing we can learn from this example is maybe now you can see why in physics it's convenient to use acceleration to mean speeding up, slowing down, and changing direction of motion. It's because now you can see that those three phenomena that might have seemed very different are actually very closely connected. Hopefully here you can see that when an object is more difficult to speed up, it's also going to be more difficult to slow down, and it's also going to be more difficult to change its direction of motion. We can see that from the example of the bowling ball, which is more difficult to speed up or to slow down or to change its direction of motion. Well, if all three of these phenomena tend to change simultaneously, then it makes sense to give them all the same label. So maybe now you can see why in physics it's convenient to give the same label, acceleration, for all three of these phenomena. They might have seemed like three very different phenomena, but you can see they tend to change together. An object that's more difficult to speed up is also more difficult to slow down and also more difficult to change its direction of motion. So it's convenient to give all three of these phenomena the same name in physics, acceleration. So we can summarize what we've seen here. The bowling ball contains greater material, which means more material, which means we say it has a greater mass, and that's reflected in the idea that the bowling ball is more difficult to accelerate than the marble. It would be more difficult to speed up the bowling ball, it would be more difficult to slow down the bowling ball, and it would also be more difficult to change the bowling ball's direction of motion. But remember, there's still another effect we have to consider from an increase in mass. Objects that have greater mass also feel a greater downward pull from the Earth's gravity. And we just want to see that from this example. How could we see that from this example? Well, imagine holding the marble motionless in your hand. So now we're doing a different experiment. Rather than thinking about the marble and the bowling ball rolling along the floor, now imagine holding the marble motionless in your hand. Now, it would be pretty easy. That would be pretty easy to hold the marble motionless in your hand. You would have to exert a small effort because the marble does feel a small downward pull from the Earth's gravity. It has a small weight, but it's a small weight, so it wouldn't take much effort to hold the marble motionless in your hand. Now let's consider holding the bowling ball motionless in your hand. Well, you could do it. You could hold the bowling ball motionless in your hand, but we know that you would have to exert a much greater effort. It would be much more difficult to hold the bowling ball motionless, and that is because the bowling ball would feel a much greater downward pull from the Earth's gravity. The bowling ball has a greater mass, which is reflected in a greater weight, which is reflected in a greater downward pull from the Earth's gravity. So you would have to exert more upward force to cancel out the bowling ball's weight to hold it motionless. So that example illustrates that objects that contain more material, that have greater mass, like the bowling ball, those types of objects really do feel a greater downward pull from the Earth's gravity. That's why it's more difficult to hold the bowling ball motionless in your hand than to hold the marble motionless. So there's the other effect of the bowling ball's greater mass. It also feels a greater downward pull from the Earth's gravity. And can you see from this example that this effect is conceptually completely separate and distinct from this effect? These are two separate, conceptually different effects. A rolling bowling ball is more difficult to speed up or slow down or to change its direction of motion. That shows that the bowling ball is more difficult to accelerate. And the bowling ball also feels a greater downward pull from the weight force. That's also true, but it's a completely separate effect from the fact that the bowling ball is more difficult to accelerate. After all, when you're holding the bowling ball motionless in your hand, you're not trying to accelerate it at all, are you? When you're holding the bowling ball motionless in your hand, you're not trying to accelerate it at all, so this effect would not be relevant. But you can still feel a difference between the bowling ball and the marble, because even when you're not trying to accelerate the bowling ball or the marble, if you're just trying to hold them motionless in your hand, you still need to counteract the downward pull from the Earth's gravity on the marble or on the bowling ball. Okay, so I hope this example shows you that an object that contains more material, like the bowling ball, that has a greater mass like the bowling ball, would experience two differences from an object that has a smaller mass, like the marble. The bowling ball with greater mass is more difficult to accelerate, more difficult to speed up, slow down, or to change its direction of motion. And in a separate effect, the bowling ball with greater mass also feels a greater downward pull from the weight force, from the Earth's gravity. Two separate effects of increasing, of the fact that the bowling ball has a greater mass than the marble does. And again, this shows us that mass is a difficult and subtle concept. It's a difficult and subtle concept because the mass has two different separate effects on the behavior of objects, as we've seen here. Now we want to try to apply these ideas about mass to the specific problem that we're working on. So again, let's imagine that we redo this problem with a block that has a greater mass while we hold the other three givens constant. So that would be a block, redoing the problem with a block that contains more material. Now we know that one effect of that is that the block will be more difficult to accelerate. The more massive block will be more difficult to accelerate. In physics, acceleration could mean speeding up, slowing down, or changing the direction of motion. But we know that on this particular problem, the object is slowing down. So in this particular problem, if the block is more difficult to accelerate, that means the block will be more difficult to slow down. The block will be more difficult to slow down. Now, the block would also be more difficult to speed up or change its direction of motion, but I'm not writing those down because they're not specifically relevant for this specific problem. In this problem, the block is slowing down. Now, what's going to be the effect of that on a sub x? Well, remember that the magnitude of a sub x measures the rate at which the block is slowing down. The magnitude of a sub x measures the rate at which the block is slowing down. If the block is more difficult to slow down, then a sub x would tend to decrease. The block would be slowing down at a smaller rate because it's more difficult to slow down. So at first, this makes it seem like maybe we made a mistake. The problem says that changing the mass should leave the magnitude of a sub x unchanged. But we just predicted that an object that has greater mass would be more difficult to slow down, and so the magnitude of a sub x should decrease. Does that mean we made a mistake? Well, no, because we haven't considered this other effect of changing the mass. Maybe this other effect of changing the mass can cancel out the first effect. So the first effect is that the more massive block will be more difficult to slow down, and we'll have a smaller magnitude of a sub x, a slower rate at which it would tend to slow down if you consider this effect by itself. By the way, notice here that we're focusing on the effect on the acceleration in the x component, because a sub x measures how quickly this object is slowing down. And we don't need to worry about the acceleration in the y component for this problem, Because for this problem, we know that a sub y is 0. So theoretically, the massive object would also be more difficult to accelerate in the y component. A more massive object would also be more difficult to accelerate in the y component, but that's not relevant for this particular problem, because on this particular problem, the object is not accelerating in the y component. So for this particular problem, we only have to consider the effect of the mass on making it difficult to accelerate this object in the x component. Now let's shift to this other effect. An object with greater mass also, in a separate effect, would feel a greater downward pull from the Earth's gravity. If we redo this experiment with a more massive block, it'll feel a greater downward pull from the Earth's gravity. It'll have a greater magnitude of the weight force. But we know that that means that it would also experience a greater magnitude of the normal force, because the normal force has to cancel out the weight force to prevent the object from moving down through the surface of the table. So the weightier object will feel a greater normal force. And remember, the normal force is the connecting link between the y component and the x component. The weight affects the y component, but the normal force is determined in the y component and also affects the x component through the friction. When there's a greater normal force, the object will feel more friction. With a greater normal force, the object will feel a greater magnitude of friction. That's reflected in this formula for the magnitude of friction. We already considered that earlier. So the normal force links the effect on the y component from the weight with the effect on the x component from the frictional force. But remember, it's the friction that is slowing this object down. So with more friction, the object would tend to slow down at a faster rate. And again, we're measuring the rate at which the object slows down by the magnitude of a sub x. So with more friction, you would expect that the object would tend to slow down at a faster rate. Let me restate this logic more intuitively. With a greater mass, the object would feel a greater downward pull from the Earth's gravity. That means that the block would press more firmly against the floor. That's what this is reflecting. The block is pressing more firmly against the floor. But common sense tells us that when an object presses more firmly against the floor, it will feel more friction from the floor. And that again would mean that it would slow down at a faster rate. So now we can see why a sub x was actually unchanged when we increased the mass, because the mass has two opposite effects, and apparently they perfectly cancel each other out. Apparently it looks like these two effects of changing the mass will perfectly cancel each other out, so that overall a sub x will be unchanged. This result from the mass would tend to decrease the magnitude of a sub x. This result from the mass would tend to increase the magnitude of a sub x. It appears that these two effects will exactly cancel each other out, so that overall the magnitude of a sub x will be unchanged. And that explains why it made sense that the mass did not ultimately appear in this expression. Changing the mass does not affect the magnitude of a sub x, because it causes two effects on a sub x that turn out to exactly cancel. Now, we could not necessarily have predicted that these would exactly cancel just by looking at these words. We'd have to look at the mathematics to see that the two effects are exactly equal and cancel each other out. Let me try to explain these ideas a little bit more intuitively one more time. An object that's more massive will weigh more, so it'll feel a greater downward pull from the Earth's gravity, and it'll press against the floor more firmly, so it'll feel more friction. A more massive object ends up feeling more friction. A more massive object ends up feeling more friction, which tries to slow the object down. But a more massive object is also more difficult to slow down. So the more massive object is feeling more friction trying to slow it down, but because it's more massive, it's also more difficult to slow down. It turns out that those two effects exactly cancel each other out, and overall, the more massive object slows down at the same rate as the less massive object. I'll say that one more time. Because the more massive object weighs more, it's going to press more firmly against the floor, and it's going to feel more friction. There will be more friction on the more massive object trying to slow the block down. But because it's more massive, the block is also more difficult to slow down. And those two effects exactly cancel each other out so that overall the block slows down at the same rate. Now, how do we know that these two effects are actually exactly equal in size and that they're going to cancel each other out? We can't tell that these would exactly cancel just from looking at what I have written here. You'd have to look at the math to see that these two effects would exactly cancel each other out. Well, here's the math where we can see the two effects of the mass exactly canceling each other out. Remember, we know that one effect of the mass is that it makes the object more difficult to accelerate. And we've said that that's reflected on the right-hand side of the Newton's second law equation. So here we have the mass on the right-hand side of the Newton's second law equation, which represents the idea that a more massive object is more difficult to accelerate. But we also know that a more massive object is going to weigh more and feel a greater normal force and therefore experience more friction. And that's reflected by the mass on the left side of this equation. You can see that mass also ended up on the left side of this Newton's second law equation. This reflects the idea that an object that weighs more will ultimately feel a greater force of friction. We can see that the mass ended up influencing the force of friction on the object. So we can see that the mass really has two different effects on the object from the fact that the mass appears two different times of this equation, on the left and the right. And we can see that those two effects of the mass really are going to exactly cancel. They cancel in this step. This is the step where basically we cancel the mass from the left and from the right side of the equation. At this point, we saw that it was legal to cancel the mass from both the left and the right side of the equation. And so this is the step in the mathematics that demonstrates that the two counteracting effects of the mass exactly cancel each other out mathematically. And that's the reason why in our final expression, the mass no longer appeared as a term in our final expression. It wasn't because the mass plays no role in the problem. The mass plays two important roles in the problem, but it turns out that the two, you can see that in this line, but the two important roles that the mass plays in the problem happen to exactly cancel each other out so that the mass did not appear in our final expression for a sub x. This is a great example of how you don't have to figure out all these ideas and interrelationships while solving the problem. You didn't have to think about these difficult and subtle ideas about the mass while solving the problem. In fact, you probably should not try to puzzle out these relationships while you're solving the problem. That's probably only going to lead to confusion. You can leave it to Newton's second law. We left it to Newton's second law to figure out the relationships, to figure out the different effects of the mass for us. And Newton's second law figured out for us that the mass was going to have two effects which would exactly cancel each other out. Newton's second law figured that out kind of for us automatically as we did the algebra without our even having to think about it consciously. That's the power of the Newton's second law approach. It allows you to come up with the correct answer without having to understand or think through all these relationships on your own. But when you have gotten a result from the problem, when you've gotten a result, it is good to step back at that point and think about whether the result makes sense in order to try to check your result and to deepen your insight into the physics concepts. And that's what we're doing right now. So now we've demonstrated from looking at the math from Newton's second law that these two opposite effects of changing the mass really do exactly cancel each other out. And so overall, the mass has no effect on a sub x. And now we can see, which is exactly what our answer would have mathematically predicted. So now we can finally make a check mark to show that this result is confirmed over here. All right, so now we've thought about each of the four givens, and we've determined that the role of each of these four givens in this expression, what's mathematically implied by our expression about the givens, also matches what would make sense. We worked out each of those here. Notice that we worked out each of these by writing down small little thought steps. So if you want to go through these types of logic, I really encourage you to follow this approach of writing down your thought steps. People think much more clearly when they think on paper rather than thinking in their head. So if you want to try to go through this type of logic, try to write down your thought steps. And notice we didn't just write down the thought steps, but we broke the thoughts up into lots of little steps. Again, people think more clearly when they try to proceed one little step at a time. people think more clearly when they make tiny little thought steps rather than trying to attempt giant thought leaps. So don't make thought leaps, make small thought steps, and write down each of the thought steps on paper. So the type of notation and approach that I used here is a good type of notation for you to imitate when you're trying to think through this type of logic on problems. Remember, this is not logic that you use to solve the problem. You should not use this type of logic to solve the problem. When you're solving the problem, you don't worry about how the different factors interact with each other. You just fill out your free body diagram and your force table, and you let Newton's second law figure out the interactions between all the concepts for you. This is the type of thought process that you should go through only after you start to get results from your problem, when it's time to start checking your results to see if they make sense and trying to get a deeper insight into the physics of the problem. And if you do want to pursue that, this is a good notation to use for when you're trying to get a deeper insight into those concepts. Write down your thought steps and write them down in small thought steps, like we have here. We wrote out the thought steps both for what makes sense and also to an extent for what was mathematically applied by a result. We wrote out our thought steps here for what a result mathematically implied, and then here in much greater detail for what would make sense. Remember, to use these techniques, think in terms of components. For example, we saw how increasing the mass increased the downward pull in the y component, but that was linked to the frictional force in the x component through the normal force. Always try to use the exact right symbols and don't use the word it. That basically means always label every single concept that you're thinking about, both in your head and on paper. Label every single concept with the exact right name or the exact right symbol. Here's what you should avoid. This would be the bad way to think about things. This seems pretty obvious. It's useless to say that this thing is getting bigger, or this is getting rougher, or this is getting faster, or there's more of this, or there's no effect of that, or this is greater, or this is bigger, or this is smaller, or this is unchanged. It's useless to say all those things unless you label what you're talking about at each point. Without a precise label, it's useless to say whether things are getting bigger or smaller or having no effect. Now this, I hope, seems perfectly obvious, but even though this should be obvious, this really is how many students actually think about physics, because they allow themselves to use the word it, and they don't force themselves to always label things with the exact right symbol or name. So students very often actually do just say it got bigger, or it got smaller, or it became more difficult, or it was unchanged, and they don't even realize that they failed to label exactly what it is they were thinking about. Or sometimes even when students write things down on paper, they don't label specifically enough what it is they're thinking about. So remember, this is the bad approach. This is the bad approach, of course, to have on paper, but would also be a bad way to be thinking about things in your head. Try to make sure that your thoughts in your head are not like this. Try to make sure that all the thoughts in your head are labeled with a specific symbol or name so that you know exactly which concept you're thinking about at each point. So here we can start putting in all those labels that we left out. We have to put in these all those missing labels, otherwise none of these changes are going to be intelligible to us. Okay, so this is a much more useful way to think about physics. This is a more useful way to write down your thoughts, and this also is much more useful if you have these thoughts going on in your head. Don't say that it got bigger, so that got bigger, so this got bigger, so that got bigger, so this got bigger. Say, G got bigger, so the magnitude of the weight got bigger, so the magnitude of the normal force got bigger, so the magnitude of the frictional force got bigger, so the block slowed down faster, so the magnitude of A sub x increased. When you're thinking about these things in your head or writing them down on paper, always try to use a precise and correct label. Either a label that uses words and names, or as I have done in some of these steps, or a label that uses the exact right symbol. That's one of the keys to improving your physics skills. I hope that the analysis that we've gone through here will give you a better understanding of the concepts of mass and weight. Many students don't really understand mass and weight, or what the difference is between mass and weight. Remember, we want to understand how these terms are used in physics. In ordinary language, people might use the word weight to mean pretty much the same thing as the word mass, but they don't mean the same thing in physics. So what are the meanings of these terms in physics? Why do we have two separate symbols here? One for the mass and one for the magnitude of the weight. Well, remember, in physics, the mass is loosely defined as the quantity of material in an object. We've loosely defined the term mass as the quantity of material in the object. On the other hand, the weight force represents the downward pull on the object from the Earth's gravity. The weight force in physics refers to the downward pull on an object from the Earth's gravity. Of course, if you were doing an experiment on a different planet than the Earth, then the weight on that planet would represent the downward pull from that planet's gravity. Or if you did an experiment on the moon, then the weight force would represent the downward pull from the moon's gravity. Well, I hope you can see that these two definitions are conceptually very separate from each other. Conceptually, the quantity of material that is contained in an object is a completely separate issue from the downward pull on the object from the planet's gravity. That should help you to see why in physics we find it helpful to use two different names for these two different concepts, because conceptually they're quite different. Now, they're certainly closely related, though, because from this formula we can see that objects with greater mass will also have a greater weight. Objects with greater mass have a greater weight, and that matches our everyday experience. Our everyday experience is that objects that contain a greater quantity of material also feel a greater downward pull from the Earth's gravity. A bowling ball contains a greater quantity of material than a marble does, and a bowling ball also feels a greater downward pull from the Earth's gravity than the marble does. That's reflected in this formula that says that increasing the mass will always increase the magnitude of the weight. Increasing the mass will always increase the magnitude of the weight. In fact, this formula says that the weight is directly proportional to the mass. Doubling the mass will double the weight. Tripling the mass will triple the weight. Cutting the mass in half will cut the weight in half. Because the weight and the mass are so closely related, it still might seem like we don't really need two different names for the two different concepts. If the only way that we can increase the weight is by increasing the mass, then is it really helpful to have two different names for these two different concepts? Well, I hope you can see from this problem why it is useful to have these two different names, because there is another way to increase an object's weight other than increasing its mass. You can increase an object's weight without changing its mass if you change g, if you take the object to a different planet with stronger or weaker gravity. That shows that the weight is more than just the mass. So if you do this experiment with a particular block on the Earth, and then you take that block to a different planet, and you do the same experiment with that same block on a different planet with different gravity, then on that new planet there will be a different value for little g, and that block will have a different weight, even though it's the same block and it has the same mass. Of course, if you take a block from one planet to another planet, its mass doesn't change because its quantity of material doesn't change. If you take a block from the Earth to the moon, the block still has the same mass on the moon because it has the same quantity of material on the moon. But the block will have a smaller weight on the moon because the moon has weaker gravity, and therefore the moon has a smaller little g. That example really shows you that mass is not the same thing as weight. It is possible to change the weight without changing the mass. You can change an object's weight without changing its mass by taking that same object to a different planet with a different strength of gravity. We saw the relevance of that in this analysis. If we redo this experiment on a planet with stronger gravity, the block will slow down faster. That's what we saw here. If we redo this experiment on a planet with stronger gravity, the block will slow down faster. But on the other hand, if we redo this experiment on the same planet with an object that's just more massive, then there will be no effect on the block, and it'll slow down at the same rate. And again, this really, I think, shows us that it's useful to have different concepts for weight and for mass. If we increase the mass of the object, then the object will weigh more, but it will also be more difficult to accelerate. And those two effects will cancel, and overall, the magnitude of the acceleration will be unchanged. On the other hand, if we redo this experiment on a planet with stronger gravity, in that case, the object will weigh more, but it will have the same mass as before. The object will weigh more, but it'll have the same mass as before, and in that case, there will only be one effect. There will only be one effect, which is that the block will slow down faster. So there is a way to increase an object's weight without increasing its mass, and that way is to transfer the object to a planet with stronger gravity, and that demonstrates that it's useful to have separate concepts for weight and mass. Not only are the weight and mass conceptually different, but they're different in real life. In real life applications, it's possible to increase the weight without changing the mass. We can do that by moving to a planet with a different little g. That demonstrates that it's possible to change the downward pull on an object from gravity. It's possible to change the downward pull on the object from gravity without changing the quantity of material in the object. We can change the downward pull from gravity without changing the quantity of material in the object if we transfer the object to a different planet with a different strength of gravity. Therefore, the weight and the mass are not just conceptually different, but they also can behave differently in real-life examples. Okay, so like I said, I hope that I know that thinking through these issues is challenging. These are challenging, difficult, and subtle issues, but I hope that one of the payoffs from this is that you'll feel that you're starting to get a deeper insight into the meaning of mass and the meaning of weight and how they differ from each other. Remember again, we're trying to understand how these concepts are used in physics. In ordinary language, maybe in ordinary language, people use the word weight to mean the same exact thing as mass, oftentimes. But what we care about here is how these terms are used in physics, and I hope that these considerations have helped you to get a deeper insight into how these terms are used in physics and why we need these two different terms in physics. As I said, I hope that you feel that you're getting greater insight into these ideas, but you shouldn't feel frustrated if you don't feel that you have complete insight. Let me emphasize that the ideas and concepts that we're dealing with in this video are difficult, challenging, subtle issues. These are issues that took scientists and philosophers hundreds, maybe thousands of years to puzzle out. People spent hundreds of years thinking about these issues and making almost no progress because these issues are so difficult and subtle and challenging to think through. So in your physics class, you go through in a few weeks and a few months concepts that took hundreds and thousands of years for scientists to puzzle out in real life. So you shouldn't expect to get complete understanding in just one sitting, so to speak. These are ideas that you have to live with over time. As you live with these ideas and think about them over and over in different contexts, you will gradually get steadily increasing understanding and insight into the concepts. Understanding and insight of these difficult and challenging concepts does not happen all at once from any one sitting or from any one video, such as this one. We're just trying to contribute to your gradually increasing understanding and insight into these concepts. But that understanding and insight into these difficult concepts takes time. This video that you're watching right now is quite lengthy because I know these are difficult concepts and I know that it takes time for these ideas to sink in. But even though this is a long video, you still shouldn't expect to have complete understanding of these concepts after even this one long video. Understanding happens over days and weeks and months, over an extended period of time as you think about these ideas over and over in different contexts. Now, we have seen from this analysis that for a sliding object, increasing the mass does not change how quickly the mass is slowed down by friction. For a sliding object, changing the mass does not change how quickly the object is slowed down by friction. Now, I want to compare this to another phenomenon, a separate phenomenon that you should be familiar with. You should know from your physics class that heavier objects don't fall faster than lighter objects. Heavier objects fall at the same rate as a lighter object. And I just want to take a little detour to show that that's based on the same logic. The same logic that indicates that a more massive object is not slowed down more quickly by friction. That's the same logic that shows that a heavier object falls at the same rate as a lighter object. That's not directly relevant to this particular problem that we're talking about, but it's still some interesting physics. So let's talk about that a bit. Imagine dropping a marble and a bowling ball simultaneously from the same height. If you drop a marble and a bowling ball simultaneously from the same height, which one will hit the ground first? And the answer is they're both going to hit the ground at about the same time. Your intuition might say that the bowling ball should hit the ground first, but it actually doesn't work that way. If you actually drop a marble and a bowling ball at the same time, the bowling ball will actually hit the ground at about the same time. You probably don't want to drop a bowling ball, you damage the floor, but if you can try this experiment on your own with two moderately heavy objects. For example, you could try dropping, say, a book and a pencil. The book was probably weighs substantially more than the pencil. But if you drop both the book and the pencil, you'll just be able to see with your naked eye that they both hit the ground at about the same time. Now, the fact is that because of air resistance, there would be a slight difference in how fast they fall. But actually, for most objects, for many situations, the effect of air resistance is going to be pretty close to negligible. If you dropped a marble and a bowling ball from a moderate height, the air resistance actually would be, I think, fairly negligible, and they both really would hit the ground at about the same time. And again, you can try this on your own by dropping a book and a pencil. If you drop a book and a pencil from a moderate height, I think you'll be able to see with your naked eye that air resistance is actually close to negligible in that case, and they both do hit the ground at about the same time. And if you were to drop them both in a vacuum where there was no air resistance, they would hit the ground at precisely the same time. All right, so as usual in physics, we're going to ignore the effects of air resistance here, and as I said, air resistance often really is close to zero, or fairly negligible in many practical situations. How is it that a heavier ball falls at the same rate as the lighter marble? Why does a heavier object fall at the same rate? As I said, it's the same logic that we saw for the sliding object. So let's go through that logic. So the bowling ball is more massive. The bowling ball is more massive. It contains more material. And we know that one effect of that is that the bowling ball feels a greater downward pull from the Earth's gravity. It weighs more. Therefore, gravity will be trying harder to pull the bowling ball down. Gravity will be trying harder to pull the bowling ball downwards, and that would tend to increase the rate of acceleration of the bowling ball. That would tend to increase the rate of acceleration of the bowling ball. This is why you might think that the bowling ball should fall faster. You might think that the bowling ball should fall faster because it's feeling this greater downward pull from the weight force. But that intuition is mistaken because it doesn't take into account the second effect of the mass. We saw from our analysis of the sliding object that there's a second effect on more massive objects. More massive objects are also more difficult to accelerate. An object that contains more material, like a bowling ball, is simply more difficult to accelerate. Now we know that acceleration could mean speeding up, slowing down, or changing direction. If you drop two objects into free fall, then gravity will be speeding them up. So in this particular application, being more difficult to accelerate is reflected in being more difficult to speed up. So the more massive bowling ball will be more difficult to speed up. And that would tend to reduce the magnitude of its acceleration. And just like with the sliding object, you can see that these two effects on the magnitude of the acceleration are opposite. It turns out that they exactly cancel each other out. These two effects will exactly cancel each other out. I'm not going to go through the precise mathematical proof that they exactly cancel, but it's quite similar to the mathematics for the sliding object. It turns out that these two effects will exactly cancel each other out, and as a result, the more massive object has the same magnitude of acceleration as the less massive object. The magnitude of the acceleration in free fall for the bowling ball is the same as for the marble. Again, this analysis would be completely true for dropping things in a vacuum where there's no air resistance. But this analysis is actually fairly accurate in many practical situations where air resistance can be treated as close to negligible. So the logic is that the bowling ball is feeling a greater downward pull from the Earth's gravity. The Earth's gravity tries harder to speed up the bowling ball than the marble. The Earth's gravity is trying harder to speed up the bowling ball than the marble. That's why the bowling ball weighs more. That's why it's harder to hold the bowling ball motionless. The Earth's gravity really does pull harder on the bowling ball. The Earth's gravity really is trying more strenuously to speed up the bowling ball than it is to speed up the marble. But the bowling ball is also more difficult to speed up because of its greater mass, and those two effects cancel. One more time. The Earth's gravity is pulling more strenuously on the bowling ball. The Earth's gravity is trying more strenuously to speed up the bowling ball than the marble. But the bowling ball, because it's more massive, is also more difficult to speed up. And those two effects cancel each other out, so that when you put them together, the bowling ball, the acceleration of the bowling ball due to gravity is the same as the acceleration of the marble due to gravity. That's why we can say, what would be a sub y in free fall? What is a sub y in free fall? Well, you should know it's little g, 9.8 meters per second squared. The magnitude of the acceleration due to the Earth's gravity near the surface of the Earth is 9.8 meters per second squared. And the key thing is, this is the same number for both the bowling ball and the marble. We use the same little g for all objects regardless of their mass. And this is why. This is why we can use the same little g for all objects regardless of their mass. More massive objects are pulled down more strongly by the Earth's gravity, but more massive objects are also more difficult to accelerate because of their mass, and those two effects cancel, so that more massive objects end up accelerating due to the Earth's gravity at the same rate as less massive objects. The marble will be accelerated by the Earth's gravity at 9.8 meters per second squared, and the bowling ball will also be accelerated by the Earth's gravity at 9.8 meters per second squared. To keep this simple, I've been talking about the case of free fall where we just drop two objects, but you could go through a similar analysis for any type of projectile motion. The same analysis would show that the magnitude of the acceleration for any type of projectile motion will be 9.8 meters per second squared, regardless of how heavy the object is. Remember that in free fall, gravity is trying to speed up the object. If you drop two objects, gravity will try to make them fall faster and faster. So in the free fall example, the magnitude of a sub y measures the rate at which gravity is speeding up the object. In this example, the magnitude of a sub y measures the rate at which gravity is speeding up the object. In our friction example, we used the magnitude of a sub x to measure the rate at which friction was slowing down the object. But in this free fall example, we use the magnitude of a sub y to measure the rate at which gravity is speeding up the object. But remember that speeding up and slowing down are both types of acceleration. So so it's not surprising that they both end up being analyzed in much the same terms. Okay, so as I said, this example of free fall is not directly relevant to the particular problem that we're working on, but I think it's helpful for our physics understanding and insight to see the parallel here. So there's an interesting parallel between friction slowing down a sliding object and gravity speeding up a falling object. The rate at which gravity can speed up a falling object is the same regardless of the mass of the object because of this logic. Gravity pulls harder on more massive objects, but more massive objects are also more difficult to speed up. So overall, the magnitude of the acceleration due to the Earth's gravity is the same for all objects regardless of mass. And similarly, for this example of a sliding object, In this example of a sliding object, friction is trying to slow down the sliding object. And we saw that the rate at which friction slows down a more massive object ends up being the same rate at which friction would slow down a less massive object. A more massive object would weigh more and press more firmly against the floor, and a more massive object would therefore feel more friction. But a more massive object is also more difficult to slow down, and those two effects would cancel each other out, so that overall a more massive object would be slowed down by friction at the same rate that a less massive object would be slowed down by friction. Well, we've now completed a very thorough analysis of this expression for a sub x in this video and in the main video. A sub x is negative here because the acceleration is pointing left, and that's because friction is pushing to the left. And because that direction is anti-parallel to the velocity, the effect of the friction is to slow the object down. Then the magnitude of a sub x tells us how quickly the object is slowing down. The magnitude of a sub x tells us the rate at which the object is slowing down. And this expression tells us that there's two things that we could do to increase the rate at which the object is slowing down. There's two things that we could do to make this object slow down faster. For one thing, we could redo the experiment on a rougher floor. If we redid this experiment on a rougher floor, represented by a larger mu sub k, the object would slow down faster. The magnitude of a sub x would be bigger. If we redid this experiment on a rougher floor, the object would slow down faster at a greater rate with a greater magnitude of a sub x. But the other thing that we could do to make the object slow down faster is to redo the experiment on a planet with stronger gravity. If we redid the experiment on a planet with stronger gravity, there would also be a greater magnitude of the acceleration due to gravity, a larger little g. And that would mean, again, that the object would slow down faster. The object would slow down at a greater rate with a greater magnitude of a sub x. Because on a planet with stronger gravity, the object will press more firmly against the floor, and therefore it'll feel more friction from the floor, and therefore it'll get slowed down faster. On the other hand, we can see that nothing else affects how quickly the object slows down. For example, the object's initial speed has no effect on how quickly the object slows down. So if we redid this experiment with an object that was moving initially more quickly, it would still slow down at the same rate as if an object that started with a smaller initial speed. If you redo this experiment with a greater initial speed, well, the speed of the object has no effect on friction. The speed of the object has no effect on friction, and therefore the speed of the object has no effect on how quickly the object slows down. That's why v sub naught did not appear in this expression. Also, what if we redid this experiment with a more massive block? What if we redid this experiment with a block that contained more material, a more massive block? Well, that would still not change how quickly the block slows down. A more massive block will slow down at the same rate as a less massive block. Now, if the block is more massive, it will weigh more, and it'll press more firmly against the floor, and it will feel more friction. A more massive block would feel more friction, but because it would be more massive, it would also be more difficult to slow down. So a more massive block would feel more friction trying to slow it down, and a more massive block would also be more difficult to slow down. Those two effects would exactly cancel. And the upshot is that if we redid this experiment with a block that was more massive, it would slow down at the same rate as a less massive block. That's why mass does not appear in this expression. So this expression tells us that the only two things that we could do to make this block slow down more quickly are redo the experiment on a rougher floor or redo the experiment on a planet with stronger gravity. Changing the initial speed or changing the object's mass would have no effect on how quickly the object slows down. That's the meaning of this expression. And we've tried to show why that meaning makes sense. So we've now completed a fairly thorough analysis for why this result makes sense. But remember, of course, this was not the final answer to the problem. This was just an intermediate result that we got while we were solving the problem. The problem was asking us for the distance. So this expression was our final answer for the problem. So what we want to do now is complete our analysis for this final answer. We already did some work in the main video for why some aspects of this answer make sense. And now we'd like to finish that work and finish our analysis for why the form of this expression for our final answer for the problem makes sense. Well, here is the work that we already did in the main video for trying to interpret this result for capital D. So we've already seen in the main video that it makes sense that v naught is ended up on the top of this fraction and mu k ended up on the bottom of the fraction. So what's left for us to check? Well, we have to check the other givens. Does the role of little g in this fraction make sense? And what about the mass? The mass was also a given on this problem, so why didn't the mass appear in this result at all? Why doesn't the mass affect the distance traveled? So let's go through the steps of checking into those issues. So first of all, we have to ask, what does our result mathematically imply about little g and the mass? So suppose that we did the experiment of increasing little g while holding v naught and mu k and the mass constant. Well, just like mu k, little g is on the bottom of this fraction. So if we increase little g, that will increase the bottom of the fraction. But when you make the bottom of a fraction bigger, you make the whole fraction smaller. So same analysis as for mu sub k. If we increase little g, our result implies that the capital D will get smaller. And what's mathematically implied here about the mass? If we increase the mass, what effect will that have on capital D? Well, the mass does not appear in this expression at all. So if we increase the mass, but we hold the other three givens constant, then there should be no effect on capital D. That's what's mathematically implied by our result. If we increase the mass and hold v naught, mu k, and little g constant, since the mass does not appear in this fraction, this result implies that increasing the mass will leave capital D unchanged. That's what's mathematically implied by our result. Now we have to check whether those predictions make sense. Do these results that are implied by our mathematical result, do they match common sense? Let's think that through. And as usual, we're going to want to think that through by writing down little thought steps. Just like previously in this video, we've been writing down little thought steps for each step of the analysis. We want to write down some little thought steps for analyzing what would make sense if we change little g and the mass. So let's suppose, again, that we imagine redoing the problem, rerunning the problem, but this time when we rerun the problem, we increase little g and hold all the other givens constant. What does common sense imply? What does common sense imply would be the effect on the distance? So suppose we redo this experiment with a larger little g holding all the other givens constant. Well, as we've discussed, doing the experiment with a larger little g would correspond to redoing the experiment on a planet that has stronger gravity. If the planet had stronger gravity, then it would also have a larger magnitude of acceleration due to gravity, and therefore it would have a larger little g. So what does common sense tell us? If we redid this experiment on a planet that had stronger gravity while holding the other givens constant, what would be the effect of that on the distance traveled by the sliding block? And again, we want to work out each of the thought steps, step by step. Well, when we move to a planet with stronger gravity, we know that that means that on that new planet, this object will have a greater weight. Remember, we're holding the mass constant, so we're using the same mass in this new experiment. Well, if the object has the same mass, but it's on a planet with stronger gravity, it'll have a greater weight. That should be obvious from common sense, but it's also clear from the formula for the magnitude of the weight, that if we increase little g, that will increase the magnitude of the weight of the object. So when we redo this experiment on a planet with stronger gravity, the object will have a greater weight. That is, the object will feel a greater downward pull from the new planet's gravity. Now, the weight operates vertically in the y component, but we want to know what's going to happen to the distance, which is measuring a distance in the horizontal x component. So how could the weight in the y component affect the distance in the x component? Well, we've already discussed this issue. We've seen that in problems that involve friction, the x and the y component are linked through the concept of the normal force. The normal force is determined in the y component, but it also affects the friction in the x component. And we'll see that same logic play out here. Because the weight is greater, so the weight will be trying with more effort to pull the object down through the surface of the floor, and the normal force will have to increase in magnitude to cancel out that weight. The normal force will have to increase in magnitude to cancel out the greater weight to prevent the object from starting to move through the table. So that would show how the normal force is determined in the y component. But then the normal force is going to affect the x component through the friction. With a greater normal force, there will be a greater magnitude of friction. We can see that from our standard formula. A greater magnitude of the normal force leads to a greater magnitude of friction, and that also matches common sense. The greater magnitude of the normal force here indicates that the object on this planet with stronger gravity, the object would press against the floor more firmly. With greater gravity, the object would press against the floor more firmly, and common sense tells us that when the object presses against the floor more firmly, that would lead to more friction. And if there's more friction, I think it makes good sense that the block would travel a shorter distance before coming to a stop. Greater friction would bring the object to a stop in a shorter distance, and that matches the mathematical prediction from our result. So the prediction that would make good sense matches what we would predict mathematically from our result. And again, we've seen that in problems with friction, there's a connection between the y component and the x component of the analysis. They're linked through the normal force. Stronger gravity would lead to a greater weight in the y component, which increases the normal force determined in the y component, and then that normal force will also affect the x component through the effect of the normal force on friction. So if you had happened on this problem to have come up with this answer, hopefully you would realize this was mistaken. Hopefully you would realize that it doesn't make sense for little g to end up on the top of this fraction for distance. We've just gone through the logic that shows that it makes sense for little g to end up on the bottom of the fraction for distance. It would not make sense for little g to end up on the top of the fraction for distance. And hopefully if you got a result like this, you would realize that you had made a mistake in your setup or in your mathematics. So our result here is that if we redid this problem on a planet with stronger gravity, the block would be pressing more firmly against the floor, and therefore it would feel more friction from the floor, and therefore it would travel a shorter distance. I think that gives us a deeper insight into these physics concepts. Well, now that we've completed the analysis for little g for this result, we have to now think about the analysis for the mass, little m. So we've already seen what is mathematically implied about the mass from this result. The mass does not appear in this result, and that mathematically implies that changing the mass while holding the other givens constant should have no effect on the distance that the object slides. Now we have to ask whether that matches common sense. We have to go through each of the thought steps to see why it makes sense, that changing the mass has no effect on the distance that the object will slide. You might want to pause the video and see if you can come up with those thought steps on your own. So let's imagine redoing this problem with a greater mass while holding the other three givens constant. Now, we've actually already gone through the most important parts of this analysis already. We've already seen that if we increase the mass, we can expect the magnitude of a sub x to be unchanged. That's what we worked out up here. We saw that if we increase the mass, that actually has two opposite effects that happen to exactly cancel each other out, so that overall the magnitude of a sub x is unchanged. We went through that logic previously, so we can just reuse that logic here. Increasing the mass should leave the magnitude of a sub x unchanged. Now remember that the magnitude of a sub x on this problem represents the rate at which the block is slowing down. Well, if the block is slowing down at the same rate with a greater mass as with a smaller mass, then there's no reason for there to be any change in the distance that the block will travel either. So we predict that increasing the mass will have no effect on how far the block slides, and I can make a check mark to show that that matches what was mathematically implied by our result. Our result did not include a term for the mass, and now we can see that makes good sense. That's because changing the mass has no effect on the distance that the block travels, because actually changing the mass has two opposite effects that happen to exactly cancel each other out. Let me just go through all that logic one more time, since that's interesting and difficult and subtle logic. So remember that if we redo this problem with a greater mass, on the one hand, a greater mass will have more weight and will press against the floor more firmly, and so it'll feel more friction. With greater mass, the object will feel a greater force from friction, trying to slow it down. But on the other hand, because it has a greater mass, it will also be more difficult to slow down. Those two effects we saw mathematically exactly cancel each other out, so that overall, with the greater mass, the object will still slow down at the same rate as before. And if it's slowing down at the same rate as before, there's no reason for the distance it travels to change. Remember that here we're imagining increasing the mass while holding the other givens constant. So we're imagining an object that's more massive, but that, for example, has the same starting speed. Well, if it has the same starting speed and it's slowing down at the same rate, if it has the same starting speed and it's slowing down at the same rate, then there's no reason for the distance that it travels to be changed. When we do this experiment, we imagine holding v naught, mu k, and little g constant. Here I've written out those thought steps a little bit more explicitly. A more massive object would weigh more, would press against the floor more firmly, and would feel more friction. A more massive object feels more friction trying to slow it down, but because it's more massive, the object is also just more difficult to slow down. And those two effects cancel, so that overall it slows down at the same rate as the less massive object. A sub x unchanged, and therefore the distance that the object slides will be unchanged, even though the mass is greater. And again, that's consistent with what was implied mathematically by our result. Notice again that here we followed the advice of putting down our thoughts on paper in small, little thought steps. When you're thinking through these ideas, write down your thoughts on paper in small, little thought steps, as I have here, writing down each of the little thought steps. And remember again, this is not a type of thinking that you would use for solving the problem. We don't use this type of thinking for solving the problem. This is a type of thinking that we go through when we finish the problem to check if our results make sense and to get deeper insight into the concepts. At this point, it's good to write down the effects of each of the concepts on each other, all the interactions in these small little thought steps. Of course, the thought steps are only useful if you label each thought step carefully. Make sure that you label each step with a precise word or symbol, or label or name or symbol that says exactly what you're thinking about at each step of the thought. So we've seen that this result does make sense. It makes good sense that v naught was on the top of the fraction. It made good sense that mu k and little g ended up on the bottom of this fraction. And it made good sense that the mass does not appear in the fraction at all. We've seen that each of those aspects of this answer makes good sense when we work through the thought steps. Obviously, you would not have time to go through all of the so many considerations for an exam problem, but I hope that maybe for an exam problem you could think through one or two of the easier chains of logic here, just to check to make sure that your answer seems like it's on the right track. And of course, the more you practice these chains of logic, the more of them you'll be able to use. But even if some of these are too complicated to think about during a test, I think it can be really valuable to think about these chains of logic for your homework and practice problems. Again, to check your answers and to give you deeper insight into the concepts. I hope that you feel that you've gotten a deeper insight into many of these concepts, such as little g and mass, from the considerations that we've talked about in this supplemental video. So these results imply that if you repeated this experiment twice, once with a block with less mass and once with a block with greater mass, if you repeated this twice with two different blocks with different masses, but both blocks started at the same starting speed, then in that case, both blocks would slide for the same distance before coming to a stop. Changing the mass of the block would not change how far the block would slide before coming to a stop. On the other hand, if you redid this experiment on a planet with stronger gravity, our results implied that if you redid the experiment on a planet with stronger gravity, then you would discover that on that planet with stronger gravity, the block would slide for a shorter distance before coming to a stop, because it would be pressing more firmly against the floor and feel more friction. What if you did this experiment on the moon? Well, you should know that the moon has weaker gravity, and therefore the moon has a smaller acceleration due to gravity. And therefore, if you did this experiment on the moon, based on this, we can see that the prediction here is that the change in g is opposite to the change in d. Change in g should be opposite to the change in d. So our results here imply that if we did this experiment on the moon, because little g is on the bottom of this fraction, where there's a smaller g, we would expect that if we redid this experiment on the moon, the block would slide for a farther distance before coming to a stop. Because on the moon, the block would press against the floor less firmly and feel less friction, and therefore slide farther before coming to a stop. Remember that whenever we think about any of these thought experiments, we're imagining changing one given while holding the other givens constant. So when I imagine redoing this experiment on a different planet or redoing the experiment on the moon, I'm assuming that we're holding the floor constant, so to speak. That is, I'm assuming that we don't just take the same block to the moon. I'm assuming that we also take the same floor to the moon. So imagine transferring the entire experiment, the block and the surface of the floor, to the moon, and in that case, the object would travel a greater distance. We have to use the same floor because we're imagining changing little g while holding mu sub k constant. If we changed to a different floor surface, then that different floor surface on the moon might have a different mu sub k. So when we do this experiment of imagining doing this experiment on a different planet or on the moon, we're imagining changing to the moon or changing to a different planet while using the same block with the same mass and while using the same floor with the same mu sub k as well. That should go without saying in all these experiments. In all these experiments, we're always imagining changing exactly one of the givens while holding the other three givens constant. If you took a block with the same mass to the moon and you redid this experiment on the moon using the same floor surface that you used on the Earth, then the block would travel for a greater distance on the moon than it did on that same floor surface on the Earth. So we've completed now a thorough discussion of this expression for capital D. And now we should have a good understanding for why v naught is on the top of the fraction, why mu k and little g are on the bottom of the fraction, and why the mass is not in this fraction at all. So what is this expression really telling us? Well, this expression is telling us how we could change the distance that the block slides. How can we change the distance that the block slides according to this expression? Well, v naught is on the top of this fraction, and that tells us that if we redid this experiment with a block with a greater initial speed, it would slide farther. I think that's very intuitive. That's why v naught is on the top of this fraction. If we redid this experiment with a block with a greater starting speed, it would slide a greater distance before coming to a stop. That's very intuitive, and that's why v naught is on the top of this fraction. That's a chain of logic that I think everybody should be able to confirm and to see that it makes sense that v naught is on the top of this fraction. On the other hand, why is mu k on the bottom of the fraction? that indicates that if we redid this experiment with a rougher surface, then the object would slide for a shorter distance before coming to a halt. Again, I think that's quite intuitive. That's something, and a chain of logic that everybody should be able to confirm on this result. Mu k is on the bottom of this fraction to show us that if we redid this experiment with a rougher surface, the object would travel for a shorter distance before coming to a halt. Y is little g on the bottom of this fraction. That indicates that if we redid this experiment on a planet with stronger gravity, the object would travel for a shorter distance before coming to a halt. Of course, in each of these experiments, we're imagining changing one of the givens while holding all the other givens constant. So if we imagine redoing this experiment on a planet with stronger gravity, but the same initial speed and the same mass and the same roughness of the surface, then in that case, the planet with stronger gravity will cause the object to travel a shorter distance. In all these experiments, we always imagine changing one given while holding the other three givens constant, even though I don't always remember to say that. Okay, so again, little g is on the bottom of this fraction because if we redid this experiment on a planet with stronger gravity, holding the other givens constant, the object would slide for a shorter distance. Why? Because on a planet with stronger gravity, the object would weigh more, it would press more firmly against the floor, so it would feel more friction from the floor, and that greater friction would cause it to travel less distance. So now we see why v0 is on the top of the fraction and why mu k and little g are on the bottom of the fraction. Because increasing v0 makes the distance greater, but increasing mu k or little g makes the distance smaller. Since v0 has a different effect on the distance than mu k and little g do, since v0 has the opposite effect on the distance than mu k and little g do, it makes sense that they're in opposite positions in the fraction. And why doesn't the mass appear in this fraction at all? Because if we redid this experiment with an object with a greater mass, that would have no effect on how far the object would slide. A more massive object will slide the same distance as a less massive object, as long as we hold the initial speed and the roughness of the floor and the gravity of the planet constant. Because if we make the object more massive, a more massive object would weigh more, it would press against the floor more firmly, and it would feel more friction. A more massive object would feel more friction trying to slow the block down. But a more massive object is also more difficult to slow down, and those two effects would cancel, so that overall a more massive object would slow down at the same rate as a less massive object, and a more massive object would slide for the same distance as a less massive object before coming to a halt. So there really is a lot of interesting physics packed into this expression. I'm sure that 99% of the people who would solve a problem like this wouldn't think about any of those issues, or most of those issues, when they're looking at this result. And you don't have to think about those issues, but if you do start thinking about those issues, it does give you a way to check that your result makes sense, and I hope that you're feeling that thinking about those issues has also helped us to deepen our understanding and insight into physics concepts. And now we can see that there's a lot of interesting physics packed into this result that we got on this problem. Do you see that's true of every symbolic result that you get in physics? Anytime you're doing a symbolic problem where you get a symbolic result, you could always go through these same steps of asking why each of the symbols appears in the place that it does in the expression. You can always ask yourself, if I increase the value of this symbol and I hold the other givens constant, what does my mathematical result imply would be the effect on the answer? And you can always ask whether that makes sense. Going through that process always gives you a chance to check your answer and a chance to get a deeper insight into the physics. Of course, some of these chains of logic are difficult and subtle, so you might not always want to think about the role of every single symbol in every single answer. But I certainly would encourage you to try to think about some of the symbols in some of your symbolic answers. Sometimes the symbols are pretty easy to think about. I think this chain of logic was pretty easy to think about, and I think this chain of logic was pretty easy to think about. I would hope that most students would actually try to think through the logic behind these two concepts and get some insight into this. These two chains of logic were a lot more challenging, but if you're willing to put in the time and effort to work through these, I think there's a good payoff in greater physics understanding from thinking about those more challenging issues. Those issues are challenging. There's a reason why this was a long video. This was a long video because those are challenging and difficult issues to think through. I'll mention we still haven't completely worked out every single possible meaning of this expression. You could certainly do more work to understand this expression in even more depth and even more insight. I'm not going to go into that any further here, but you could. For example, why is v naught squared, whereas mu k and little g are just raised to the first power? They're not squared. Why is v naught being squared? Do you see that because the v naught is squared, that means that v naught has a greater effect on the distance than mu k and little g? For example, if I doubled mu k, that would cut the distance in half. And if I doubled little g, that would cut the distance in half. But if we doubled v naught, because it's getting squared, the distance would be quadrupled. Because v naught is being squared, if you double v naught, the distance would be quadrupled, not doubled. That's why I say that the square means that, in a sense, v naught has a greater impact on the distance than mu k and little g. I guess to be more precise, what I should say is changes in v naught. Changes in v naught affect v more than changes in mu k and little g do. Doubling mu k or doubling little g would cut the distance in half, but doubling v naught would quadruple d because of this square. Why is that? Why does v naught have more effect, or it has two different effects on the distance? V naught can affect the distance in two different ways, and that's why it gets squared here. Well, I'm not going to go into that. I'm not going to explain why this term is getting squared, but that's an interesting issue that you might want to ponder on your own. I guess I'll give you a little hint about that. Really, mu k affects the distance in one way, and little g affects the distance in one way. But increasing v naught would actually increase the distance in two different ways. Increasing v naught would give us a greater starting speed, and that would lead to a greater distance by two different paths. There's two different reasons why having a greater starting speed would lead to a greater distance. And since increasing v naught leads to a greater distance by two different paths, that explains why changes in v naught have a bigger impact on the distance, and why v naught is being squared in this expression, while the other terms are only being each raised to the first power. So if you want to puzzle this through, you should ask yourself, why does increasing v naught increase the distance in two different ways? What are the two different ways that increasing v naught would increase the distance? As I said, I'm not going to go into those issues anymore in this video, but that's something that you could think about on your own if you wanted to continue to go into even deeper into deepening your physics insight and understanding into these concepts. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge of $1 or more at my Patreon page. You can visit my Patreon page by clicking the link on the screen or by using the link in the video description box. Thank you.